Welcome back to the third part of lecture 14. So in the previous part, we learned how to convert pretty much all three formats of instruction to machine code. So now let's take a look at how we can do the complete conversion of all instruction codes. So now the question is, since we know how to convert instructions from MIPS to zeros and ones, so now how about we can convert zeros and ones back to machine code, and then eventually we convert that back to C code, kind of like how the CPU is trying to understand our code. Okay, so how can we do that? Okay, so for each instruction we have 32 bits, and of course we look for the first 6 bits because it tells us whether this is an R format, I format, and J format. Remember what is the opcode for R format? Yes, R format is 0. And then for J format, you have 2 or 3. And the rest will be for I format. So if you are not familiar with that, you can go to the MIPS reference sheets that I just posted online at CAD Courses. Then you can see the opcodes of different types of instructions. And once we know the format of the instruction, we can partition the instruction bits into the correct field. And then once we write down the values of each field, then we can reconstruct the MIPS code. Now, when we have the MIPS code, we can convert that MIPS code into a valid C code. And is it possible? And do you think the C code will be unique? And let's find out. Okay. Here I have 6 machine instructions. Okay. There are 6 lines, and each line is one instruction in machine code. And I'm writing them in, instead of zeros and ones, I'm writing them in hexadecimal so that it's easier for us to read. But of course, from hexadecimal, we cannot really tell what kind of instruction it is because they are in hexadecimal. So what can we do? We need to convert them to binary. So let's do it, and you can pause the video and do the conversion by yourself. And then once you're done, you can resume the video and then take a look and see whether you get the right conversion. Okay, here is the list of 6 machine code in binary. Do you get them right? Hopefully you do. Okay, so now what do we do next? We have 6 instructions. Of course, instructions are run line by line. So if you want, you can convert them line by line, or since we have the binaries all together, maybe we can do the conversion all together. So first of all, what is the next step? Yes, we need to find out what format by identifying the opcode. So how many bits are in the opcode? 6 bits, right? So if opcodes are 0, then you have R format. If opcode is 2 or 3, then you have J format. And if the opcode is 1 or 4 to 62, then you have I format. All right, so let's do it together. What is the format of the first instruction? R. How about the second one? R. Third one. So what is this value? 1004, right? So it's I format. How about the fourth one? 0 means R format. And the next one, 10008, right? So it's I format. And finally, the last one, you have 2, which is J format. And now, since you know that each instructions are in a particular format, the next thing is to partition the instruction based on the correct format. So for R format, you have 6 fields. I format, you have 4 fields. And the J format, you have 2 fields. Okay, and within each field, all you need to do is to decode a binary to base 10 so that you know what the numbers are. Okay, so here is the base 10 value. And of course, it doesn't make sense to convert the J format target address into base 10 because eventually we are not going to use this number, right? So it's okay to keep them as base 16 or base 2 binary so that eventually we will get the right address. But let's forget about that first. Let's take a look at the other instructions because those are all more important. So for example, for our format, the first line, you have RS. Remember where is RS? Okay. RS is here, right? So for R format and I format, this column is RS, this column is RT, this is RD, this is shift amount, and then this is the function code. Okay, so based on the opcode and the function code and the field of registers, we can perform the translation into MIPS. And again, the translations between MIPS and the zeros and ones are one-to-one, which means that every single instruction is unique. So you won't have multiple instructions being converted into the same zeros and ones. Okay, so once we perform the conversion, we have instructions like this. Okay, so you have the R format correspond to the address, I format, R format, I format, and J format. And look at this one. The address of the J instruction doesn't make sense because the address here looks like this, right? But this is the address, kind of weird, right? But if you think about it, remember how many bits are stored in the address for J format? Is it 32 bits? Is it really 32 bits here? No, right? We only have 26 bits. So what can we do? We need to add 20 at the end and the first 4 bits of your address to here, which means that you need to add pretty much 4 zeros in front of it and then add 2 zeros here. And now once you have the 32 bits, this will be a different address. So don't worry about that. We'll talk more about that later. Okay. So if you try it, add 4 zeros in the front, add 2 zeros in the end, you get what? You get this address. Okay, so give it a try because this is 1, right? And you add 2 more at the end, you get 4, which is this 4. Okay, so try it and you see that the address is gonna be this one, which means that when you see the jump, it actually jumps back to this line and continue. All right. So now use a label instead of the address so that we can see clearly the flow of the program. So I label it again. After you calculate the address, actually it goes back to here. So I can give a name loop as this label. And what about this exit? Why is this exit here? So let's go back to the last slide and find out what happened. Okay, BEQ. What does this 3 do? Remember, we just learned that in the last part of the lecture. 3 means starting from the next line of this branch instruction and count 3 more lines. 1, 2, 3, which is the next line of jump. And that's why in the next line of jump, I put the label exit, which means when the content of T0 equals to 0, I'm gonna branch to exit so that I don't have to go back to the loop. So this is actually a loop now. Okay. Now, once we have this assembly language, the next job is to create a C code. And again, because C code is higher level, it can take some creativity. So what I would suggest you to do is to go over what these instructions do. Take a look at the overview of the behavior and then write out the equivalent C code. Okay, so don't translate them one by one. Otherwise, it's going to look awkward, especially with the BEQ and the J. All right, so try to think about or observe the behavior of this code and then now write an equivalent C code. Okay, so after you do the encoding and do the mapping again, because from MIPS instruction, you don't have variables. So you try to create new variables to map with your registers. Okay. So now I assume this pairing, and now what you need to do is just to translate it. Okay. So you can see that this is a while loop, or it is a loop. Okay. When the value T0 is not 0, you continue, right? So basically, and then you keep on comparing A1. So what is A1? A1 is an input argument, right? So you keep subtracting 1 from A1, okay, until is less than 0, right? And then you exit. So this is how you do it. And then here you just keep adding A0 to your current sum. So it is kind of like a loop to sum up A0 A1 number of times. So, and that's why I give it the name of multiplication, because you are just keep adding the multiplicand n number of times, right? The multiplier time. And then every time you do the sum, you subtract 1 from it so that you can count how many times you are adding the sum. Okay, so this is how we convert the machine code into the equivalency code. Okay, so now let's go back to the LUI. Remember what LUI does? Do you remember that? Yes, LUI is to copy a 16-bit value into the upper portion of the register. So this is called LUI. Okay, so for example, we use the same example, right? We have a 32-bit immediate, and we know that there's no way we can convert this line into zeros and ones, because the immediate itself is 32 bits already. There's no way we can put this into a 32-bit instruction, and that's why we need the LUI. And what does the LUI do again? We take in the upper 16 bits, so you need to cut this number into half. Take the upper half and use LUI to save that into the upper half of AT register. And then you use the OR operator to copy the lower half into the lower half of the add register. And at the end, now the register add, or register AT, I should say, will contain the whole 32 bits. And now you can add this to the register 0 using an R format. So whenever you have an immediate greater than 16 bits, all you need to do is to use the LUI instruction along with ORI instruction and save that immediate into a register. And now you convert the original instruction into an R format. Okay, so this is LUI. Okay, and you may think, since we're going to deal with a lot of large immediate, wouldn't it be nice to have this kind of operation automatically done? Yes, we do. Okay, so whenever the number is too large, actually the simulator, the Merced that we use, will automatically convert it. So which means that it's okay to code in Merced using this instruction, even though we cannot convert that into zeros and ones. But Merced can actually later on break it down into these 3 lines of code and then convert them into zeros and ones. So this is done automatically in Merced and a lot of MIPS simulator or assembly simulator. Okay, and that brings us to the new term called pseudo instruction. So pseudo instructions are instructions like this example that cannot be converted into zeros and ones right away. You have to break it down into the true assembly language that can be converted into zeros and ones. Okay, so as I just mentioned, right? True assembly language. What is true assembly language? So basically, true assembly language does not have pseudo instruction. As I mentioned, pseudo instructions are instructions that cannot be converted into machine language right away. So only the true assembly language instruction can be converted into zeros and ones machine code directly. Okay, so any instructions that cannot be converted into zeros and ones we'll consider as pseudo instruction. Okay. So what happened to the pseudo instructions then? Okay. So basically the simulator, or we call it assembler, get the proper term because that's the program that takes in the assembly language and assemble them into zeros and ones. So this is called assembler. Okay. So there are several examples that are pseudo, so you can use them in your Merced if you want. Okay. So the first one, move. Move is to move the content of register 1 into register 2. And you can see that this is a pseudo because one thing is that we can use an existing MIPS instruction to represent that. Okay. And also it's not really following 1, 2, 3, 4 format. Okay. So this is a pseudo. So what is the equivalent true assembly instruction? So I'm going to copy what's in register 1 to register 2. So what would you do it? Yes, we just use add, right? We add what's in register 1 to 0 and save the result into R2 or register 2. So this is the equivalent of move. But in your program, probably you can use move. I never used it before, but you can try it. How about this one? Load immediate. So I'm going to load the value, which is a constant, into a register. Okay, so again, this is a pseudo because it's not really following the convention format 1, 2, 3, 4. And also, we have existing instruction to actually do the process, right? So that's why this is not real or true instruction. So now, how do we use the original true assembly language instruction to represent it? Okay, so I'm loading this immediate, right? So basically same thing, we use add-i. But again, this value can be less than 16 bits and can be more than 16 bits. So we have two scenarios. If the values can be fit into 16 bits, we just use the regular add-i. Okay, so because this can be encoded into the machine code. So you add the value into 0 and save the result into register. But what if values does not fit into 16 bits? What can we do? What if this number is bigger than 16 bits? What can you redo? Yes, we have to use LUI again. So we grab the upper 16 bits of the value, again, only upper 16 bits. So you have to cut the numbers into 2. And then save it into the upper portion of the register. And then use the ORI to copy the lower portion and save it into the register. And now your register contains the original value. And now you can use the add-i again. I mean, not add-i, sorry. You can use the add because it's going to be our format. All right, so let's take a look at the next example. Okay, so low address, because a lot of times we will declare variables in MIPS. Okay, so for example, in your Merced, right, you have the data portion. You can actually create variable n equals to a number. But in the instruction, you have to load that value. So one way to do it is to load the address that stores that variable. Okay, so in this case, I'm going to load that address. Okay, so giving you the label where the number stores, for example, n. Okay, then now you can load the address. Okay, and then the address will be stored into a register. And now you can use load word with the register to actually load the number from that address. Okay, so it's equivalent to adding the label value to 0 and saving the register. Of course, that label, if it can fit into 16 bits, of course you can do it. But most of the time, the address is always greater than 16 bits. So you will, again, need to use LUI again. Okay, so what you need to do is save the upper half of the address into register, and then use the OI to save the lower half of the address into the same register. And now you have the whole address. And even in the end, the register will contain the same address value as LA. Okay. So from this example, you can see that when we break down a pseudo instruction, we need to use an extra register to store a temporary value. Okay. So from the previous example, we see that we can use the same register, but it may not apply to all kind of pseudo instruction, because sometimes you may not be able to reuse the same register. So what can we do? And in this case, we will use a special register called AT, and we have used it in one of the examples before. Okay? So and that's why in the register convention, I told you that you shouldn't use AT or register 1 in your program, because this is reserved for the assembler to break down the pseudo instruction. So make sure that you don't use that. Otherwise, when the assembler breaks down a pseudo instruction, your AT will be overwritten. So make sure you don't use AT. Okay. Okay. So let's take a look at another instruction. Okay. So this is called rotate right instruction. What it does is giving you a register. Okay. It contains 32-bit value. Now you're going to rotate it to the right, kind of like shift. Okay. So you shift right by the value number of a month. For example, if the value is 5, you shift by 5. But doesn't mean that you pad the leading bit with 0 now. All you need to do is actually copying these 5 bits to the front. So this is called rotation. So what does it do? Yes. What you're doing is you are shifting right, okay, with value amount of bits, right? So you shift the register by value number of bits, okay, and then save it into AT. But the moment you do that, these bits will be gone, right? So what can we do? Now, you shift this, okay, register to here, okay, so that you maintain this, but now you keep that into the most significant bits. Okay, so let me use another screen to show you what happened. Okay, so let's switch screen. Okay, so let's say I have this register, right? I want to shift this amount of bits. Okay, so first of all, I have register AT, which is SRL, right? So what I'm going to do is the register AT will contain, to make it easy to read, maybe we do this. All right, so I'm going to shift my register value number of bits, right? So at the end, I will have something like this, and these are all 0. Okay, so I don't know how many, depends on the number of bits, right? So basically, I'm shifting this, okay, to my least significant bit, okay? And now I do the SLL, and I save it as REG. So now I'm actually overwriting this original register. Okay, so what am I shifting? I'm shifting it by 32 minus value, which means that this is value, right? And this is 32 minus value. So I'm shifting this portion by this amount of bits. Okay, so now my new register will contain the original last few bits, and these are all 0s. Okay, so now finally you use the OR operator. And what do you get? You get something like this. Oh, I did it wrong. This should be this direction, right? Because it's the last few bits. So I will have something like this. And then I have something like this from the AT. So now you perform the rotation. So was it good? Okay, so if you're a little bit confused, you can rewind the video and take a look at the example again. Okay, so let me go back to the screen now. Okay. So let me make sure that the screen is shared. Okay, good. Okay, so now let's continue. Okay, so again, here is another instruction called no op. So what does no op do? It's not an operation. Basically, you're just doing something that the CPU won't create a meaningful result. For example, I'm shifting the 0 register by 0 bit and save it as 0. Of course, you cannot save anything into register 0. But what it does is to kind of like store the CPU and stop the CPU from doing anything. Okay? And in the next class, CSE 140 architecture, you're going to see how we're going to use no-op in the CPU design. Okay? So don't worry about that for now. Okay? And sometimes the program or the simulator will try to detect your operation or instruction with wrong operand and try to make it into pseudo instruction. So for example here, is it the correct operator? How many say yes? How many say no? Take a look at it. What format is it? R format, right? But here, is it following R format? No, this is a register, but this is an immediate, right? So you should have I here. But sometimes when you type this code, your mouse actually will try to interpret it and then treat it as pseudo instruction. And how does it work? Okay, so it should be, again, NIU, right? But instead you use ADU. So at this moment, your mouse program will try to understand it. Okay, so it will translate it into NIU if the value is less than 16 bits, right? Just as we mentioned. But if the value is greater than 16 bits, it will use the LUI again. Okay, so it will get the upper 16 bits and save it into the add register, the register 1. Use the lower 16 bit and save it into your lower part of the add register. Okay, so that's your value, right? After these two lines, you have your value stored into a register. And now you can use the ADU, which is correct. Okay, so basically, in your MIPS assembler, usually the assembler has a list of pseudo instruction. So it will try to compare those instruction operator and see whether it will work. Okay, and we call this kind of instruction or assembly language MIPS assembly language. So basically, when we talk about MIPS assembly language or MAL, we're talking about the program written with instructions that are pseudo. Okay, so just keep that in mind. If you write a program and it contains pseudo instruction, we call that assembly language MAL or MIPS assembly language. Okay, and when you write a program that contains only true instruction, which means that it doesn't contain any pseudo instructions, we call that true assembly language. Okay, so which means that every single line of that program will be converted into unique zeros and ones. The assembler won't need to break down your program. So this is called true assembly language. Okay. Yeah, so if a program contains MIPS assembly language, the assembler needs to go into these instructions and break them up and then convert them into true assembly language before it can translate them into zeros and ones. Okay. So again, how does the assembler or the simulator recognize pseudo instruction? Usually they have a list of predefined instructions that they can follow, and sometimes it will detect whether you use a wrong operand. And if the operand does not match the operator, it will try to see whether breaking it up will work. Otherwise, it will just give you an error. Okay. So here's an example of true assembly language. And now let's see whether we can convert that into MIPS assembly language. So this is a creative process because you can always use a new instruction or operator to describe that. Okay. So how do we do that? So in this case, I color code them so that for each color, I will use one pseudo instruction to describe that. Okay. So for example, here, I can say I'm copying value 0 into V0, right? So all I need to do is just load the immediate 0 into V0. And then this one is a little bit tricky. I'm comparing whether 0 is less than A1. If it's not true, I'm going to exit. So I'm comparing 0 is less than A1. And if it's not true, I'm going to exit. So what does that mean? I'm actually comparing what? Whether A1 is greater than or equal to 0, right? Yeah, so I will use larger than or equal to 0. Okay. And then if it's true, then I will exit. And then this is the same. And then again, since we cannot do sub I, but we can use a pseudo again to create an instruction that will subtract 1 from A1. So again, MAL language is more flexible, but it depends on whether your assembler or your MIPS simulator can understand your instruction. So be aware of it when you try to code. Make sure that you pick the right operators that your assembly programming language or the assembler can understand. Okay. Okay. So here's an example again. So which one is MAL and which one is TAL? So the first line, at I T0 T1 40,000, is it a MAL or TAL? Who say it's MAL? Who say it's TAL? So let's think about it. Can you fit this into 16-bit? No, right? Because 16-bit, you can only go up to 32,000. So this is a MAL. How about this one? Is it a MAL or TAL? Who say it's MAL? Who say it's TAL? Are you sure? So let's take a look at it. I'm comparing whether this equals to this. And then if it's true, I exit. So can you see any problem with that? Yes, this is an immediate. For a regular true assembly language, branch statement contains 2 registers, not 1 register, 1 immediate. So yes, both of them are MAL. Very good. All right, so in this section, we learn how to deassemble simple instructions by using the opcode. Once we know the opcode, we know which format they are. And then now we can, based on the format, and partition the field. Okay. And when we need to convert that into higher level languages such as C, we can be creative. First of all, take a look at the overview behavior of the program and then write the equivalency code. And in assembly language, we categorize them into true assembly language and MIPS assembly language. When we have MIPS assembly language, it also contains pseudo instructions. So make sure that the assembler will try to break down the pseudo instruction into true instruction or the real instruction before convert them into zeros and ones. Okay. All right, so I think that's it. And I will post the next lecture pretty soon. So again, when you have time, try to revisit this video as many as often, and so that you can get a better idea of this topic. And if you have any questions, email me or come to my office hours.